Hello everyone, my name is Jiangpeng He. It is my pleasure to present our most recent work grading and reweighting towards imbalanced class-incremental learning. The objective of imbalanced class-incremental learning is to learn new classes incrementally from non-uniform data distribution, such as the long-tail distribution. This non-uniform distribution poses an unique dual imbalance challenge, where we have the interface imbalance between the stored exemplars and the new task data, which is also a common target for the existing class incremental learning work with uniform data distribution. However, in our case, we also have the interface imbalance issue that within each individual task. This dual imbalance issue could potentially lead to overfitting, underfitting, as well as catastrophic forgetting during the class-income learning process. In this work, we look into this issue from the perspective of gradient update. Our method is motivated by the observation that the magnitude of the weight update is significantly biased towards instant-reach classes. So here we have the equation for weight update for each iteration I and learning rate eta. We conduct a preliminary imbalanced classical learning experiments for learning 3 new tasks incrementally, with each task contains 5 classes. We can see that the gradient magnitude is proportional to the number of training data, which varies a lot between and within the tasks. The idea of our method is to reweight the gradient to balance the optimization process for all classes. We will first talk about the interface gradient reweighting, assuming that there is no previous task learned, and then we will generalize it to the interface gradient reweighting for imbalanced class-income learning case. As shown in this equation, we propose to multiply a class balance ratio alpha to balance the gradient matrix before we are doing the backpropagations. However, often the proper alpha is challenging as it relates to complicated optimization and learning process. Therefore, in this work, we propose to calculate this ratio based on accumulated gradient magnitudes over the iterations to guarantee a balanced optimization over the learning process. So before we dive into the interface case, we would like to point out an observation of imbalanced catastrophic forgetting issue, where the head classes suffers more forgetting than the tail classes, as shown in this figure in the left-hand side, because most of the training data of head classes becomes unavailable in the subsequent learning phases due to a fixed and limited memory budget per class. In other words, for tail classes, if we are able to store almost all the data from them for knowledge replay, then there may not be any forgetting issue for those classes. So the knowledge distillation is a representative work to maintain the learned knowledge. However, the traditional knowledge distillation loss treats all the classes evenly so that it may not be very effective for the imbalanced case. Therefore, in this work, we also introduce a distribution-aware knowledge distillation loss to prioritize the maintaining the knowledge for the head classes. So our DAKD loss decouples the original distillation into 2 parts using an imbalance ratio sigma, measured by how much training data is lost for that class during the classical learning. Therefore, in the case of balanced data distribution where sigma equals 1, the DAKD loss perform equivalently as the original knowledge distillation. When the sigma decrease, it will introduce more regularization on the classes with more training data lost. So the idea of our method to address the interface imbalance issue is to first reweight the gradients for new tasks and learn tasks separately by following the same strategy we used for the interface reweighting. And we multiply a task ratio R here to balance the learned task and the new tasks. Then we leverage a loss balance ratio beta to strike a balance between the plasticity, which is the gradient from the cross-entropy loss, and the stability. with the gradient from the distillation loss. So finally, our weight updated equation is shown below, which addressed both the interface and the interface imbalance challenges for the class-incremental learning. So we conduct comprehensive experiments on the long-tailed version of CVPR100, ImageNet subset, and Food11 datasets. Our method achieved promising results under both learn from scratch and learn from half experimental protocols with different step sizes. It is also worth mentioning that our method is designed in an end-to-end fashion without requiring decoupled training stages compared to existing work. This can also facilitate its application in the real-world scenarios. We also evaluate the effects of our method in terms of learning unbiased classifier weights. As shown in this figure, the weight norm of the baseline method varies among the learned classes, so this results in significant biased predictions. And the existing method mitigate the interface imbalance issue, but still having variance within each individual task, and our method by directly balancing the learning process, achieving a uniform classifier that could also explain our promising results for the imbalanced classical learning. So for more experiments and details, please refer to our paper and supplementary materials. Our source code is now public. You can access it by scanning this QR code. And for any question regarding this paper and project, please feel free to send me email. Thank you for watching the video.